8 minutes ago, while you were scrolling, cooking, answering a message, something happened on a dark mountaintop in Chile. A tiny patch of sky brightened, flared, and began to fade again in less time than it takes to finish this paragraph. On the summit of Cerro Pachón, the sensors that will belong to the Vera C. Rubin Observatory caught it. A pinprick of light that should not have changed that fast, in that color, in that part of the sky. Within seconds, software compared tonight's image to thousands of earlier ones. One pixel had climbed from invisibility to outshining millions of normal stars, then started sliding back down again. Its color shifted from blue-white to a duller glow, like a camera flash seen through fog. The system flagged it as an alert, the kind of ultra-fast transient theorists have only begun to predict, and our current telescopes almost never catch. Most of the missions you have heard of, even famous NASA observatories, would have missed it completely. Their cameras stared deeply at narrow fields, or returned to the same galaxy only after days or weeks. By then, this event would be gone, its story reduced to a single blurred frame, if anything at all. Right now, we do not know what caused this hypothetical flash. Is it the death of a strange star, a compact object feeding for a heartbeat, or something no model has described correctly? And if a brief pulse like this can appear and vanish between ordinary human moments, what else crosses our sky unseen? Unknown explosions, orphaned signals, even small, dark rocks on inconvenient paths? To understand how we even saw this at all, we have to go back to a decades-old idea that almost did not get built. And that story begins with a mirror. That flash on a Chilean mountaintop, and the instrument preparing to catch the next one, are exactly the kinds of stories we follow here. I'm Mohammed Afnan, and this is The Hidden Cosmos, where we go past clickbait into what space missions are actually built to do and what their data really say. Every episode, we unpack the hardware, the physics, and the stakes for life on this planet, without dumbing the science down or pretending NASA has confirmed something it hasn't. Rubin is only one of the observatories we will be tracking as their first discoveries start pouring into scientific announcements over the next decade. So if you want to watch this unfold in real time, subscribe and turn on notifications. To understand why astronomers are nervous and excited about this telescope, we need to revisit that supposedly still night sky. For most of human history, if you walked outside at night and looked up, the message seemed obvious. Nothing up there ever changes. The same constellations rise, cross the sky, and set in the same patterns your grandparents and their grandparents saw. Stars might glitter, planets might wander a little, but on a human timescale, the heavens look carved into stone. Early astronomers turned that feeling into mathematics, treating the stars as fixed reference points painted on a vast, distant sphere. Even when we started aiming serious telescopes at the sky, that picture hardly budged. The great observatories of the 20th century took long, careful exposures of distant galaxies and nebulae, masterpieces of still photography. When the Hubble Space Telescope launched in 1990, its most famous images were also single, exquisite frames. The pillars of creation, the Hubble Deep Field, spiral galaxies frozen in perfect symmetry. If anything changed in those scenes, it was expected to happen over years, centuries, or longer. Even when we did study change, it was usually the slow kind. Astronomers compared images taken months or years apart to track how a supernova remnant expanded, or how a variable star brightened and dimmed over long cycles. Instruments in space, from Hubble to Chandra and Spitzer, were scheduled like visiting specialists. They would drop in on a target, take a few snapshots, and move on, rarely watching anything continuously, closely. The first digital sky surveys followed the same logic. Point a telescope at a patch of sky, stare for a long time, catalog every faint smudge of light, then move on. Repeat that process enough times and you can build an atlas of the universe. Implicit in this strategy is a quiet assumption. Most stars simply sit there. Explosions like supernovae are rare, dramatic accidents that you either stumble across by luck or deduce later from the debris. In other words, most of our maps of the universe are snapshots, not movies. Imagine trying to understand a city by taking a single long exposure photograph from a hilltop at midnight. You would see the streetlights, but not the cars. You would see apartment towers, but not people coming and going, not windows turning from dark to bright as someone gets home from work. You could convince yourself the whole place is calm, even sleepy. Traditional astronomy operated with that same blind spot. Our instruments were exquisite microscopes pointed at tiny regions of the sky, not wide-angle cameras filming everything at once. They were perfect for depth, terrible for speed. Then a group of astronomers asked a rude question. What if the sky is far busier than we think, and we're simply too slow and too narrow-sighted to notice? If the sky was really buzzing with brief events, then pointing ever sharper telescopes at tiny patches of darkness would never be enough. Astronomers needed something different, almost impolite by older standards. A machine built not for perfect portraits, but for relentless surveillance. In the 1990s, a small group began sketching that machine under the working name Large Synoptic Survey Telescope, or LSST. Their idea was simple to describe and brutally hard to execute. One observatory that could scan the entire southern sky, deeply and repeatedly, night after night. Instead of collecting a handful of still photographs, it would build a time-lapse of the universe. Making that reel started with the light-gathering heart of any telescope, the mirror. Engineers designed an 8.4-meter primary mirror cast together with part of the secondary and tertiary mirrors in a single block of glass. Imagine a disc wider than a city bus, polished so smooth that if it were stretched to the size of a country, the tallest bump would be smaller than a pebble. Behind that mirror sits a camera, a 3.2 gigapixel detector made from an array of tuned sensors. To picture its scale, imagine stripping the sensors out of hundreds of high-end smartphones and tiling them together into one gigantic eye. Each time Rubin takes a single exposure, that eye will capture a patch of sky so wide it could hold dozens of full moons at once. To give this system the clearest possible view, planners chose Cerro Pachón, a high, dry peak in northern Chile, whose thin atmosphere and distance from cities make it one of the darkest observatories on Earth. From there, Rubin can sweep across the center of the Milky Way and deep southern constellations that never rise for much of the planet. The observing strategy is as audacious as the hardware. Rather than locking onto a single galaxy for hours, Rubin will hop from field to field, taking snapshots 30 seconds long, then moving on. Within roughly 3 nights, it will have tiled almost the entire visible southern sky, like Google Maps repeatedly redrawing every street on a continent. Over a planned 10-year survey, each region will be revisited hundreds of times, turning those still images into a true movie of the changing universe. Every clear night, this dance will pour data down the mountain, tens of terabytes before dawn, enough to fill stacks of hard drives that would tower over a person. Software will compare each fresh frame to everything Rubin has seen before, pixel by pixel, searching for anything that moved, brightened, dimmed, or changed color. Whenever it finds a difference, the system will issue an alert, one small message in a nightly stream of millions saying, in effect, something just happened here. It is hard to reconcile that scale with the physical reality of Rubin itself, a single building clinging to a ridge, its dome not much larger than a modest sports arena. From a distance, it looks ordinary, yet every night it will watch a swath of sky, big enough to swallow all the constellations, and catch changes no human eye could ever notice unaided. Before Rubin even finishes construction, smaller survey telescopes trying a scaled-down version of this strategy have already started revealing how wrong the old textbook sky really was. Before Rubin ever opens its eye, smaller experiments have already tested the idea of a restless sky. If you want a preview of what a true sky movie might reveal, you have to look at places like Hawaii, California, and the Canary Islands, where a new generation of survey telescopes quietly began watching for things that change between one night and the next. PAN-STARRS in Hawaii, the Panoramic Survey Telescope and Rapid Response System, was one of the first. Instead of staring deep at a single galaxy, it took repeat images of wide fields, looking for anything that shifted between visits. The Zwicky Transient Facility at Palomar pushed the strategy further, using a huge camera to scan broad swaths of the northern sky night after night. None of these systems came close to Rubin's power or sky coverage, but they were like putting a single CCTV camera above a busy intersection just to see whether anything interesting ever happens. Almost immediately, they started catching things textbooks had not prepared us for. Among the strangest were events nicknamed fast blue optical transients. They rise in brightness incredibly quickly, reach temperatures hotter than many normal supernovae, and then fade again in just a few days. They are too bright and too fast to be explained by the standard story of a massive star collapsing and exploding. Whatever engine drives them burns its fuel in a furious, brief outburst. Then came 2017, and a flash with a very different kind of echo. The LIGO and Virgo observatories detected a ripple in spacetime, a gravitational wave from 2 neutron stars spiraling together. Within hours, telescopes across the world, including these survey instruments, hunted for the place in the sky where it happened and found a kilonova, a burst of light powered by colliding ultra-dense stars spewing heavy elements into space. Survey telescopes also uncovered odd flares from otherwise quiet galaxies, outbursts near central black holes that did not fit simple patterns. Some looked like stars being torn apart and swallowed, others like sudden changes in the way those black holes were feeding. Even ordinary-looking stars in our own galaxy misbehaved, flaring dramatically or dimming without warning. Remember, all of this came from instruments that watched only slices of the sky and only part of the time. It was like hanging one security camera above a single street corner and, in the first week, capturing accidents, arguments, and scenes you could not classify. If that much drama unfolds in one field of view, what are you missing on every other street? This is what keeps astronomers awake when they read the early results from PAN-S, TARRS, ZTF, and similar projects. For decades, models suggested that truly new classes of fast events should be rare, that the universe had mostly shown us its bag of tricks. There would be occasional surprises, but the basic catalog of explosions and flares was probably complete. Instead, the more we looked with rapid surveys, the more the sky behaved like a city at rush hour, not a sleepy village at night. Rubin is built to take that unsettling preview and scale it up beyond anything we have attempted. Where PAN-S, TARRS might cover part of the sky in a few nights, Rubin will sweep almost the entire visible southern sky in the same time and do it far deeper, catching fainter and more distant events. Where ZTF sends out thousands of alerts on a good night, Rubin will issue millions, each pointing to something that moved, brightened, faded, or changed color somewhere overhead. Some of those alerts will be routine, rediscovering known types of supernovae and variable stars. But buried among them will be phenomena we have never named, events so fast or so rare that, until now, they slipped completely between our exposures. For an astronomer, that is both thrilling and terrifying. You get only one chance to catch many of these in their first moments. Miss them, and they are gone forever. But catching the universe in the act is only half the story. To do it at Rubin's scale, astronomers had to solve a problem that had nothing to do with mirrors or glass and everything to do with data. Catching the universe in the act sounds romantic until you sit in the room where the plans turn into hardware and headache. After the first survey telescopes started revealing a restless sky, Rubin's team knew that simply scaling up the idea would not be enough. They had to build a machine of frightening ambition and then figure out how any human community could live with the torrent of information it produced. The mirror alone was a gamble. Casting 3 optical surfaces in one block of glass had never been attempted at this size before. If the cooling process cracked it, years of work and millions of dollars would literally fracture. Even once the glass survived, it had to be polished and measured so precisely that tiny temperature changes in the polishing hall could ruin the shape. Engineers built custom robots and test rigs, slowly nudging the surface toward perfection, one grain of glass at a time. Then there was the camera, a stack of delicate sensors and electronics taller than an adult and so sensitive that a single speck of dust in the wrong place could blind part of its field of view. Assembling it required clean rooms, custom cryogenic systems to keep the detectors cold, and rehearsed choreography from technicians who might never touch a similar instrument again in their careers. All of this had to operate on a mountaintop that occasionally shudders with earthquakes and is blasted by wind and ice. The dome had to keep dust, humidity, and temperature swings away from equipment while still opening quickly enough for a full night's observing. Support structures were modeled and remade to ensure the telescope would not flex or vibrate when it slewed from one patch of sky to another. But even if the optics and mechanics worked perfectly, there was the deeper problem: data. Rubin is expected to generate tens of terabytes every clear night in millions, on the order of 10 million. Automated alerts whenever something changes. No group of astronomers could read that many messages, let alone decide which ones matter, in real time. Without careful triage, the most interesting events would disappear into the flood. So teams of software engineers and scientists designed pipelines, databases, and machine learning systems whose job is to drink from that fire hose without exploding. It is like trying to listen for one particular conversation in a stadium of shouting people, using microphones, algorithms, and a strict set of rules about what counts as unusual. Even deciding those rules sparked arguments. If you make the filters too strict, you risk throwing away once-in-a-lifetime phenomena. Too loose, and follow-up telescopes waste precious time chasing noise. All of this unfolded under the usual pressures of big science: shifting budgets, political scrutiny, competing priorities, and the nagging question of whether such an enormous survey was really worth its price tag. At several points, Rubin could have been delayed into irrelevance or canceled outright, a footnote about an overambitious dream. That it survived to stand on Cerro Pachón is a quiet testament to human stubbornness. And yet, if they get this right, Rubin will do more than surprise astronomers. It will start changing very practical things here at home, including how safe we feel on a planet surrounded by moving rocks. Those changes are closer than most people realize. So far, we have talked about what Rubin will see: flashes, flares, new kinds of explosions. The deeper question is what those images will do for us. Others stretch far to the scale of the entire cosmos, reshaping how we picture the invisible structure that holds galaxies together and drives them apart. Start close to home. Every bright meteor you have ever seen is a reminder that Earth moves through a swarm of rocks, from sand grains to mountain-sized bodies, many of them completely unlit. We have found most of the truly giant asteroids that could end civilization in a single impact, but below that size, our catalog has dangerous holes. City-killing objects 100 meters across can still hide in the dark, following orbits we have never measured. Rubin changes that calculation by watching for motion, not just brightness. Each time it images the sky, it records the position of every faint dot. When the telescope returns a few nights later, software lays the new frame over the old one. Anything that is shifted against the background of fixed stars is flagged as a moving object, even if it is too dim to notice in a single snapshot. From a handful of such positions, astronomers can fit an orbit and project it forward, asking a blunt question. Does this rock ever cross Earth's path? Today's surveys do this work with impressive dedication, but they cover limited regions and miss objects that approach from awkward directions, like out of the glare of the sun. Rubin's deeper, wider, faster coverage should reveal many of the remaining unknown near-Earth asteroids, especially the small, dark ones that reflect little light. No observatory can promise perfect safety, yet each new orbit added to the map turns an invisible threat into a predictable neighbor. But the same repeated images that track dangerous rocks also reveal something grander, the ghostly scaffolding of dark matter. We cannot see it directly, but its gravity tugs on everything around it. When a massive clump of dark matter sits between us and distant galaxies, its pull slightly bends and distorts their light, an effect called gravitational lensing. Rubin will measure the shapes of billions of background galaxies, mapping those tiny distortions across the sky. For years, simulations of the universe suggested dark matter should form a vast, relatively smooth halo around galaxies, like a gentle fog. Better models and early lensing surveys hinted at something more intricate, filaments and knots linking galaxy clusters in a cosmic web. Rubin's statistics will be powerful enough to draw that web in detail, turning hints into an actual three-dimensional map. It is the difference between seeing only the lights of a city at night and suddenly tracing the roads and buried pipes that connect them. And beyond even the web lies an older, stranger problem, dark energy, the name we give to whatever is driving the expansion of the universe to speed up. By tracking how billions of galaxies are distributed at different distances, Rubin will help measure how fast space itself has been stretching. If that rate has changed in subtle ways, it could reveal whether dark energy behaves like a constant background pressure or something more exotic, evolving with the universe. Taken together, these three threads, asteroids, dark matter, and dark energy, turn Rubin from an impressive camera into a kind of nervous system for our species. It watches for incoming stones that could damage our world, it outlines the hidden bones of the cosmos, and it listens for shifts in the force that may eventually tear galaxies apart. Awe and unease live side by side. We are finally drawing the map of the environment we inhabit, from neighborhood hazards to the architecture of spacetime. All of this, though, depends on a fragile, human-built observatory perched on one mountain. And like every mission we have ever constructed, Rubin is already running on a countdown clock. Rubin's science goals sound grand and abstract until you put them on a calendar. Construction on the mountain has already turned blueprints into steel and glass. The concrete pier is poured, the dome rotates, the mirror and camera have survived their trials and are making their way toward installation. Engineers talk about first light, the moment when starlight finally bounces off the completed optics and lands on the camera's pixels. That milestone is expected around the middle of this decade, followed by months of tuning, testing, and gentle sky scans while software teams learn how the real telescope behaves instead of the simulated one. Only after that shakedown does the main event begin, the legacy survey of space and time, a planned 10-year marathon of imaging. On paper, it looks simple. Pick a pattern, swing the telescope across the southern sky night after night, and repeat. In reality, every year of that survey matters in a slightly different way. Early on, each new exposure is landing on territory that has never been recorded at Rubin's depth or cadence before. Every transient it finds, every near-Earth asteroid it adds to the catalog, every calibration of the camera's quirks improves the entire next decade of data. Some opportunities are literally first and only. A supernova in a nearby galaxy, a rare kind of stellar merger, or an object making its very first close pass by Earth will never present exactly the same configuration again. If we do not recognize them in time, if follow-up telescopes are busy or pointed elsewhere, that precise experiment is gone forever. We can model similar events in the future, but we will never again see that one unfold from start to finish. To avoid wasting those chances, astronomers are building a reaction system wrapped around Rubin. Robotic telescopes on other mountaintops will listen for its alerts and snap to attention when something unusual appears. Spacecraft that see in X-rays, ultraviolet, or radio will pivot their gaze within hours based on those messages. Even NASA missions not designed with Rubin in mind are being wired into this network, so that when Chile whispers, "Something happened here," observatories across the planet and above it can respond like a coordinated nervous system. This is why the countdown matters. We will only ever see the universe for the first time once. The first few years of Rubin's watch are not just more data. They are our one chance to catch certain classes of events at the moment we become capable of noticing them. Miss them now, and our descendants may have to wait centuries for the same roll of cosmic dice. Schedules, budgets, mirrors, and sensors can make this sound like another huge engineering project. Step back from the timelines and something else appears. Rubin is not just another telescope. It is a declaration that, on a small world with limited time and countless distractions, we chose to watch the universe carefully enough to see it change. For most of this story, we have been talking about hardware, schedules, and data streams. But under all of that sits something more basic, a shift in what we mean when we say the night sky. For the first humans who looked up, the heavens were the definition of permanence. Even in the early space age, with rockets flying and probes leaving Earth, the stars themselves were treated as fixed points, the unmoving backdrop to our motion. Every new instrument has chipped away at that illusion. Galileo's telescope turned wandering points into worlds. 20th century observatories revealed colliding galaxies and nebulae made from ancient explosions. Hubble showed that stars are born, live, and die in tangled nurseries, that galaxies evolve, that the universe itself is expanding. Each time, our idea of normal had to stretch to include more change than we expected. Rubin pushes that stretching down to the human timescale. Instead of hinting that things change over millions of years, it will show that the sky above one town, in a single week, is busy. Stars will flare and fade between workdays. Asteroids will shift perceptibly from one school night to the next. After a decade of that, it will be impossible to think of the sky as static. We will talk about space the way we talk about weather, storms of radiation, seasons of dust, passing showers of ice and rock. The physical telescope will not last forever. Its mirrors will age, its electronics will be upgraded, its dome will eventually host some successor or stand quiet in the wind. But the record it creates, that 10-year movie of the changing universe, will outlive its shell. Children who are learning to read today may one day become scientists mining Rubin's archive for patterns nobody has thought to ask about yet. We happen to be alive at the exact moment humanity is about to see the sky move in detail for the first time. The only real question is whether we will pay attention while this happens right in front of us. If you have watched this far, you are not just a casual viewer. You are part of the tiny fraction of people alive right now who know that, in our lifetime, the night sky is about to turn from a static backdrop into a high-definition movie. While most of the world goes on with their evening routines, a new observatory on a Chilean mountaintop is preparing to catch every flash, every flare, every passing rocket can. On this channel, we are going to follow that story in real time, from the first test images to the discoveries that make headlines years later. If you want to be here when those moments arrive, subscribe now and turn on notifications so you do not miss the next episode. We will keep unpacking what Rubin and other missions are really seeing, without the fake drama, but with all the real wonder. I would like to hear from you, too. If Rubin could answer one question for you personally about the universe, what would you want it to find? Or, if something in this video changed the way you think about the night sky, tell me what surprised you the most. And if you know someone who still thinks astronomy is just pretty pictures of frozen galaxies, share this video with them. Let them know that the sky above their house is about to start moving in ways no generation has ever watched before. Being early means you will see the first rough images, the false alarms, and the genuine shocks as they unfold. You do not need a telescope, only curiosity and a few quiet minutes today. Somewhere above you, the camera is already rolling. The universe is changing. The only thing left to decide is whether you will watch with us.